My name's Dane. My presentation's on Domain Wall-Based Spintronic Devices for Neuromorphic Computing. So, some motivation for this. Down. Motivation for this is, so AI, a lot of what AI tries to do is emulate how our brains work, and it's trying to do what our brains are like naturally good at, like object detection, reading and understanding it, and like speech detection. But it goes about this in a really different way than how our brains do it. So like a GPU would run at about 300 watts and has about like a 1 picojoule per operation of compute. But if you compare that to our brains only run at like 20 watts and about like 1 femtojoule per operation. But it's not really a fair comparison because like the operation is pretty different. There's like a synaptic event. So why are traditional computing, where the inefficiency is coming from? Mainly it comes from the von Neumann bottleneck, where the memory and compute are separated. So a lot of the data has to move a lot from memory to like the CPU to be computed. That uses a lot of energy, but also a lot of it comes from that it's synchronous. So you have like the clock tree and it's constantly switching. So that's a lot of like dynamic power consumption, and you have all the flip-flops everywhere. So that's also a lot of power leakage. So our brains use this in a different way. Instead of having synchronous, we have event-driven computation, where neurons are mostly idle, and then incoming signals are integrated slowly over time. And when it reaches a threshold, it emits a potential spike that goes down the axon to the synapse, the next neuron. And that's where you have compute and memory, where the synaptic weights store information, and that like determines how much of the spike goes in the next neuron to be integrated. And then the firing activity can change the synaptic weights. So that's how you like learn. And it like if 2 neurons fire at the same time, you can change the. So we need to like emulate synapse. So to meet this, we need a non-volatile adjustable resistance. So non-volatile resistance, we know that is the MRAM device, which can be use tunnel magnetoresistance. And for it to be adjustable, we can use spin transfer torque. We went over these concepts before, so it's just a refresher. And if you combine those two, we get this kind of device where we have the domain wall right there. Then if we send a current through it, we can move the domain wall through the spin transfer torque. And then if we do a reverse current, we can move it back. And the amount we move it by is proportional to how much charge is moved. So for a longer current pulse, it moves longer. And we can see how this affects the tunnel magnetoresistance, where when it's mainly parallel, the resistance is really low. And when it's mainly anti-parallel, the resistance is higher. Then when it's in between, the resistance is in between. So that's for the synapse part. And then for integrate and fire, we want something that kind of emulates that. So we need an adjustable state with a sharp switching threshold. So for the adjustable state, we can use the spin transfer torque again. And for the sharp switching threshold, we can use a tunnel magnetoresistance. We get a device like this. Or before, it was like one long MTJ. Now the MTJ is just right here. And it's the same concept where you have a current pulse moving the domain wall. So then you have a current pulse and it slowly moves and it slowly moves. That's integrating it. And then once the domain wall passes the MTJ, then suddenly it's no longer parallel with low resistance. Now it's anti-parallel with high resistance. So it's the sudden jump in resistance. And this can be attached to other circuitry for this jump in resistance to lead to a voltage spike. But there are some issues. So for the synaptic weighting, we want it to be non-volatile, but the domain wall would naturally drift if this was just a regular smooth rectangle due to thermal activations, and it would tend to the middle, but we want it to stay where we put it. But we also want it to be predictable by like the amount it moves from the current pulses we put in it. But random fluctuations in the material can act as pinning sites, so it won't be linear. So this paper looked at using little notches throughout the device where the domain wall wants to minimize the energy, so it wants to be as small as possible. So it will want to be in between the notches, so it's thinner. So, and they proved that it will make it more stable. So right here you can see the notched device is stays where they put it, and the smooth device moves. And it's also, since it's equally spaced notches, the domain wall movement is linear. So then we have a more linear graph right there. And if you notice this, they also had a heavy metal layer because they also tested the effects of spin transfer torque versus spin orbit torque to move the domain wall. For spin transfer torque, they'd run a current through L and R to move the domain wall, and then spin orbit torque, they run it through the heavy metal. We know how that works. And they saw that spin orbit torque can move the domain wall at lower current densities, which is better. And like discussed before, separating the read and write paths protects the tunnel barrier from the write currents. And they also showed that the spin orbit torque has more stochasticity, which is seen right here, where it's like has these random fluctuations. And this actually kind of counterintuitively, it leads to higher accuracy models because noisy learning reduces like overfitting the curve. So right here in this green lab thing, we can see that the accuracy is a lot higher than the spin transfer torque curve. Then there's also, for the integrated and fire neuron, we don't actually want it to stay where we put it because we want it to be leaky like the neurons, where the if it hasn't fired or if it hasn't had an input in a while, we want it to like slowly go back to normal. But we don't want that to happen too much because we also want it to be able to integrate. So this was done with shape anisotropy, where the domain wall would wants to minimize its energy, so it wants to go to the thinner parts. So it will slowly move back. The integrations, the spikes, the current pulses will push it that way. So they showed that, you can see in this, that the integrations push the domain wall that way, then slowly, when there's no integrations, it moves back. Then they used an interesting technique of asymmetric notches, where it gets wider going this way, where like before it was just like a notch like that. Now it gets wider going this way and smaller going this way. So it's harder to push the domain wall towards the wider part. And so that's what they want, where they want to, or they want these sites where the domain wall can hit. And then the shape anisotropy will slowly pull it back, but it won't pull it back too far because you still want it to be able to integrate. And this will actually, I forgot, an important thing for these neurons is you want it to reset back to where it was when it started so that you can fire it again. And this emulates it well with by slowly pulling it back through a multi-step stochastic resetting. So this actually emulates the neuron really well. That's it.